So now we're going to discuss a formal definition of computer science and algorithms. So we mentioned computer science is the study of algorithms, including a bunch of other things. But the things we want to focus on for this particular unit is the mathematical properties of algorithms and studying efficiency. And what I mean by that is if you have an algorithm that, let's say, is uh, sorting a million numbers, let's say you have two algorithms, algorithm one and algorithm two. Well, if algorithm one does a really good job under certain conditions, but algorithm two does a really good job, let's say when the numbers are all sorted in reverse order, uh, then you're going to want to have a way to determine which algorithm is the best to use in certain situations. And so we have a field in computer science related to algorithms and complexity of analysis. And all these algorithms get uh, run on computer systems which have hardware architectures that are designed to process bits of data or bytes of data. And we'll get into that more, I think, in chapter 4. And then the linguistic realization is really just trying to say that we have algorithms that get translated into programming languages, which are high-level languages. So an example of that would be something like C++ or Java. And then besides high-level languages, these high-level languages actually get translated into intermediate languages, and then these intermediate languages actually then get translated into what's called machine language, which are just a bunch of zeros and ones. So there's all these different layers of abstractions when you're dealing with computer systems. Okay, so why do we or care about algorithms and why is it important? Well, the reason is if we can specify an algorithm to solve a problem, that's basically saying we have some sort of description of a way to solve a problem, then you can automate its solution, meaning you can run it on a computer. So an algorithm is basically some sort of formal description of a way to solve a problem. It's like the steps to solve the problem, and then you automate the solution by writing programming code. You write code in a programming language to run on a computer. Not all problems lend themselves well to algorithmic descriptions or computer solutions. For example, sometimes you may have a solution that is inappropriate for the problem. Let's say, for example, you're trying to build facial recognition software to recognize out of a crowd of people in a public area if someone there matched the description of a person who, let's say, stole a car, and you specifically wanted to use this to arrest that person. Now, in that case, you could have situations where the person that your facial recognition software found could be innocent, and if you went to go to arrest that person, that wouldn't be a good thing to do. So you have to be careful with the types of solutions you're trying to design algorithms for. And in some cases, algorithms or trying to come up with an algorithm for a solution will be too inefficient just because of the complexity of the problem. So sometimes it's not good to always design algorithms. But it doesn't mean that you should really stop. I mean, in the real world, uh, there are a lot of hard problems out there, and it doesn't stop people from trying to do such things. You just try to come up with some assumptions and bounds and limitations as far as what your algorithm can do, and go from there. So the formal definition of an algorithm is a well-ordered collection of unambiguous and effectively computable operations that, when executed, produces a result and halts in a finite amount of time. So the things you want to keep in mind here are the things that are underlined, and those are the things we'll go over. But basically, well-ordered is a set of instructions that is ordered in such a way that it has some meaning, so that it doesn't it's not perceived as it wouldn't cause any confusion to the actual machine that's trying to translate those instructions or the person that's reading them. Unambiguous means basically the instruction is clear. Um, And effectively computable means that the operation is something which can be done in a finite amount of time, which is essentially what they mean when they say produces a result and halts in a finite amount of time, meaning that it's going to stop at a finite amount of time. It's not just going to keep going on and on and on.